In this video, I'm going to talk about Cohen's d. I'm going to explain what it is. I'm also going to show you an example and talk about some of the guidelines. Then I'm also going to talk about its relationship with Hedges g. So first off, Cohen's d is a standardized measure of effect size. And what that means is that we can interpret a standardized measure of effect size no matter what level of measurement the underlying raw scores have been measured in. And so because we speak of standard deviation units in the context of Cohen's d, it doesn't matter whether you're using interval, ratio, or any other type of scale. It doesn't matter where the data come from. As long as you can measure a standard deviation from those data, you can calculate a Cohen's d as a representation of the magnitude of effect between two means. And I mention here that it's actually the most commonly used measure of effect size to complement a t-test of the difference between two means. And here's the Cohen's d formula. So we've got the difference between mean 1 and mean 2. That difference is divided by the average of the standard deviations. So standard deviation 1 plus standard deviation 2 divided by 2. And that's what makes it a standard deviation units metric, is that the difference here is divided by the average standard deviation. So if you had a difference of 1 and the average standard deviation was 1, then Cohen's d would be equal to 1 standard deviation, right? So if you had a difference between means equal to 5.5 and the average standard deviation was 5.5, then again Cohen's d would be 1, a 1 standard deviation difference between the means. So in the glasses and perceived intelligence study, you may recall that I calculated Cohen's d at negative 0.51, and I obtained that by subtracting the faces with no glasses perceived intelligence ratings by the faces with glasses ratings means. So this mean minus this mean divided by the corresponding standard deviations for both samples divided by 2, which is the average. And that gave me essentially about half a standard deviation difference. I mentioned here that it's arbitrary whether Cohen's d is a negative or positive value. So I could have easily put the yes glasses face mean first and the no glasses face mean second, and that would have eliminated the negative value and it would have been perfectly legitimate. I just have to be sure to know how I'm interpreting the result. So if you put the no glasses mean first and the difference is negative, then you have to say something like not wearing glasses, no glasses, is about 0.51 of a standard deviation less intelligent. It's perceived to be about half a standard deviation less intelligent than wearing glasses. Conversely, had I put this mean first and the 4.03 second, then I would have had to say something like wearing glasses yields about a half standard deviation, 0.51 of a standard deviation, more intelligent ratings from the people. So Hedges g is something that I see sometimes. And so what's the difference between Hedges g and Cohen's d? Well, Cohen introduced Cohen's d for the purpose of estimating statistical power. Cohen wasn't really interested in developing a statistic to complement the t-test in studies that are published. He was more interested in developing a method to help people determine the sample size that they should use to conduct their study to achieve a certain level of statistical power, which is related to the chances of rejecting the null hypothesis if it is in fact false. So Cohen was interested in power, not so much introducing an effect size estimate. So it's interesting that we now actually use Cohen's d just as commonly to estimate an effect size from a study as we do to estimate the sample size we need to conduct a particular study. Now, that is important because Cohen's formula that he developed to represent the standardized metric of a difference between two means is technically framed in the context of population values, not sample values. That is important because Cohen's d tends to overestimate the standardized difference between two means in the population. It's a very slight overestimate, but it is one nonetheless. And so Hedges came up with a version of the Cohen's d formula that is more appropriate to use when you conduct your own study, and then with the means and standard deviations, calculate the effect size in standard deviation units for the purposes of interpreting the magnitude of the effect. There are a couple of different formulae out there that calculate Hedges G, but just to show you that it's essentially based on Cohen's d, and then there's a correction factor to account for the fact that Cohen's d tends to overestimate by a small margin the magnitude of the effect in the population. And this is the correction factor over here. So if you use Cohen's d, or Hedges G more accurately, you can interpret the magnitude of your effect across small, medium, and large. And Cohen suggested that a small effect is equal to 0.20, and that's either negative or positive. So the mean difference equal to about 20% of a standard deviation is a small effect in Cohen's guidelines. A medium effect is about 50% of a standard deviation difference between the means, and a large effect is 80% of a standard deviation between the means. Now, people interpret these effects in the context of estimating the sample size required to conduct a study with a certain level of power, but they also do it when they conduct their own study and then after the fact calculate an effect size and interpret it whether it's small, medium, and large. Now, the truth is that Cohen kind of just pulled these numbers out of thin air. They're just based on his own impression of the studies that he comes across, mostly in the behavioral sciences. So these are really, I would say, mostly in the context of what you see in the research. So a large effect of 0.80 is just not commonly observed. And so if you get that sort of effect size in your study, you could describe it as large based on Cohen's guidelines. But what exactly constitutes small, medium, and large requires a little bit more consideration than just blindly following Cohen's guidelines. And so in the Glasses No, Yes, and Perceived Intelligence study, we could categorize the effect of 0.51, standardized estimate from Cohen's d. Hedges G, you might recall, was estimated at negative 0.50, so just a very slight difference, slight reduction. And we could describe that as a medium effect, because it's really pretty much bang on medium. Now, I followed on with some description that a conventional IQ test has a standard deviation of 15. And so 50% of 15 IQ points is equal to 7.5 IQ points. And so you may also interpret effect size in this context where you're getting closer to real data and having a more real interpretation. And so whether 7.5 IQ points is important in the context of how people are going to perceive your intelligence, probably that's an impact. I would say between 1 and 2 IQ points is not very much of a difference, but getting as high as 8 IQ points is starting to actually be a pretty decent difference. So again, interpreting the effect size, Cohen's d or Hedges G, according to the small medium guidelines is useful. But even more useful sometimes is trying to break it down into another metric where you can actually talk about, say, IQ points or earnings or something else that has a scale that actually is interpretable. So you could use both the standardized effect size and unstandardized effect size estimates to help you gauge how big of an effect is.